Blackburn. I'm a rising sophomore at Hanover High School, and for my project this year, I decided to focus on designing and basically making an economical interferometer for use in a school lab environment. So this is just a quick overview of what I'm going to do. But basically, our overall goal was to build low-cost optical systems that can be used in a school environment, like I said before. And to do this, we wanted to create adjustable components that fit together to match the needs of more than one system. And these new pieces would integrate with and replace their factory counterparts without giving up much precision at a much lower cost. So basically, what is interferometry? Basically, interferometry is a measurement method that uses the interference of waves to make extremely precise measurements. And this technique uses light waves for the study of changes in displacement. It's used extensively for calibration and measurement and precision machining, and it works by splitting one light beam into two, and when this happens, an interference pattern is formed when the two beams superimpose. So basically, this is a quick diagram of what happens basically when you turn it on or when you turn the light source on. So I'm just going to read it. So basically, first, the light is emitted from the source, and then it gets split by the beam splitter in the middle. And half of the light beam is reflected, and half of it's transmitted through. And third, the beams are reflected back from the two mirrors, and then they recombine at the beam splitter. And again, half of it is transmitted from the top, and half of it is reflected from the right. And they both get reflected down, and when they reach the detector, they interfere with each other either constructively or destructively. And what that means is basically during constructive interference, the beams are in phase, which means that the peaks of each wave meet and support each other. But during destructive interference, the beams are out of phase, which means the peaks of each beam meet the valleys of the other, and basically they cancel each other out. So by adjusting the micrometer, which is just like a really fine-tuned thing that moves one mirror back and forth on the mobile arm, like a central interference pattern will emerge, and you can find the difference between the static and mobile arms. So the particular model that I used is called a white light Michelson interferometer, and the white light is made up of a lot of different frequencies, unlike a laser. So this results in an interference pattern with one central frequency, so you can see it defined by the two black lines in the center going across. And there's less defined fringes as you move toward the top and bottom. And this occurrence allows you to make an accurate measurement without any guidelines to narrow down the range of possible results. So basically, these are the two design programs I used, Fusion 360 and Cura. So Fusion 360 is a tool for product development that basically combines design and engineering. And in the middle is like a sketch design that I was able to use, basically build each part with, and that particular thing held a beam splitter cube by all four corners. And I was able to export that into Cura, which is a program that communicates directly with the printer, so you can 3D print what you design. That's pretty cool. So basically, I'm just going to go through and compare all the 3D printed parts to the machine parts. So these are all the parts that I used, or that I designed and printed. So they're we got the lens and mirror mount here, the spectrophotometer mount, beam splitter mount, mirror and lens base, and the light source mount. I'm going to go through and explain these in a second. So the beam splitter mount holds this little cube thingy that is the thing that splits the beam in two, and half is transmitted and half is reflected. And so the original design had a lot of components that you could adjust, like height and move it around, but for our purposes we really didn't need that, so I just had a thing that pinched all four of the corners and held it in place. So it only cost 76 cents to print, which is kind of nice. Okay, so the light source mount was really complicated when it started. It had, again, a lot of stuff that you could maneuver around, but Dr. Testdorfer, who was basically my mentor throughout this entire thing, said that he'd never touched those bits. He never used them. So we basically came up with this tiny little thing that basically using a screw or some tape could just hold it in, and it only cost 28 cents to print. So the mirror and lens base was made up of two parts originally, but well, this is actually just for the lens base, but we came up with one design that could be used for all three times throughout the print, 2 for a lens and 2 for a mirror holder. So it worked in tandem with this thing. So originally it had a thing where you basically screwed in a lens or a mirror, and that worked really well, but like it's hard to 3D print that. So Andy came up with something where you could have both a hard PLA plastic and a squishy, flexible polyflex material. So that's basically what held that. And I did not get a picture of the spectrophotometer mount because we didn't have that part anymore in the lab because the tester took it. But so I couldn't get a picture of that. But it wasn't that great of a design, at least like the way that he had, because basically the viewing end would just bounce up and down, and so that's just not that great. So I came with a 2-piece design that had a hole and then like a half hole. And one part held it, went over top and fit over it, and basically just screwed it in. So that's a picture right there. And that was our most expensive piece that cost $1.52 to print. Results. You guys kind of already saw this, but this was the end result of all the parts we got. This bit is not 3D printed, but it worked, so that's kind of nice. We have 2 pictures. This one just kind of shows the spectrum of light. Didn't really show the thing, but this is the full interference pattern here, and for a lot lower cost, it works just the same as the original version he brought in. So basically, in the real world, mixed light interferometers usually cost from $3,000 to $5,000, and that's a lot of money. So this is a lot more than like a lot of non-college organizations can afford, and so optics is like a super limited field of study because smaller budgets can't really spend that much money. And then they make even more money by selling these specialized parts that you have to buy their special adapters for, and then they so it's just really inconvenient for us. So the material cost of printing was about $360, which is a lot better. And the biggest expense for that were the lenses and mirrors and beam splitter because they cost a lot of money, and we couldn't print them with the 3D printer. And it was under $5 to make every part for the interferometer, so it was a lot more convenient. But there's like a lot more things to consider because the material cost isn't the only thing to worry about, because the cost and availability of a 3D printer can be a big issue because it costs like almost $4,000, I think. So, but the thing is, you can use it for like a lot more than printing just an interferometer. So we're using it around the lab. Al was printing, I think, a glove dispenser and just a lot of stuff that we'd have to buy normally. So it just makes back its cost a lot. And then another thing to consider is the time it takes to print. It takes about an hour for every piece, depending on the piece. So that's just another thing. So some other projects. Have been taken around by other labs around the country. This team built an interferometer made out of Legos, which is pretty cool. And in the future, I think I can use the past projects to kind of further improve optical systems such as this one. And yeah, questions?